Good evening,
Yes, please.
all of you. We are now at the doorstep of the third lecture of medium rise building designs and constructions. Today, Professor will be explaining under the title, the design philosophy for a medium rise building of about 10 floors. Professor Jayasinghe, we appreciate the steps taken forward to share your knowledge about this important area of civil engineering and shouldering the responsibilities as the chairman of the Civil Engineering Sectional Committee for the session 2021 and 22. Dear participants, hope you will accept what he delivers in this valuable lecture and throughout the series about designs and construction of medium and high-rise buildings. As I mentioned last time, previous day, please remember that you need to register for each session through MIS since this is a series of lectures. So enjoy the evening. Over to you, Professor Jayasinghe.
Thank you. Thank you, Engineer Kamala. Can you all hear me?
Oh, very well.
Very well. Okay. Today I'm using the phone for audio and computer for the video. So I'll be doing the lecture again on the screen on the whiteboard today as well, because there are many things to be explained, which is easier to explain on the whiteboard by drawing rather than using a PowerPoint presentation. Okay. So today again I will take an example which is similar to the example I used last time. So it's a building having a grids of 7.5 in this direction.
I think please share the screen. We can't see.
Just one moment.
No.
No, okay. No, okay. Thank you.
Okay, right. This way, we'll have 6 meters each. This way, 1, 2, 3, 4, 5, sorry, A, B, C, D, E. This way 1, 2, 3, 4, 5. So in this, now this is a 10-story building. If it's a 10-story building, generally we are allocate about 25% of the area for the service scope. So I'm planning to get lift arrangement like this. And I will have another wall here, another wall here. So these are lifts. Now, if it is a 10-story building, the first thing we have to see is whether the building can twist. Whether the building can twist. So if you take wind in this direction, that is Y direction, we have this wall.
Excuse me, Professor. Professor, excuse me.
To resist wind.
Can I disturb you for a moment?
Yeah.
Someone that they can't hear. I don't know whether I can hear you well, but
I can hear.
Some,
Some are not here, I think, but
yeah, some are there. No, they can't hear.
yeah, but they
Yeah,
are.
I
think I also can hear, I think so. Here.
Then I think let them check their laptops or whatever again.
Yeah, that's it.
Yes. Yeah, I think the mics may be muted.
Now they can hear.
Can you all hear?
Yes, we can hear, sir.
Yes, it's good.
I think most of them are here, Mr. Prof. So we can continue.
Yeah, okay.
Yeah.
So they can hear. Yes. So if you take this y direction, these walls are going to bend about an axis of because you can see the walls in this way or this way, depending on the direction of the wind. So if the axis of bending is like this, I'll put it this way. We have to see that the centroid of all these walls will lie along this axis. So what we do is we calculate x bar is equal to sigma ix divided by sigma I. Not here. And it's second order of area. Mathematically arranged. So naturally, the centroid should be on this axis. Similarly, when you take these walls, we like it to lie, the centroid lies somewhere here. So for these walls, the axis of bending will be like this. Axis of bending will be like this. So what we do is we take y bar is equal to sigma iy divided by sigma I. And when you take that direction, you have to add this wall, and this wall. And let's say the distance of the length of this wall is x1. Then you can calculate the length of that wall. And because it's a 10-story building, it's like we can go for 225 or 200 also possible. It's a little difficult to concrete. So if you go for 225 or 250 walls, then it's much easier to concrete. You lose only 50 millimeters or 25 millimeters, but still you'll find that the concreting operation is very easy. So if you take this structure, we'll have walls and columns. So if you take the length of this wall, that is 6 meters. So we have a wall like this, 6 meters of length, bending about an axis like this, and then we have column. Let's say we have selected the column size of 700 millimeter by 700 millimeter. Now, what can we say about 700 by 700 when it comes to earthquake resistance? Should be pretty okay. Why? Last time we said that the beam depth will be only 600 by 600. The width can be about 300, 350 or 400. So the beam is smaller than the column. So we don't have to worry about where the plastic hinge forms, because plastic hinge will always form within the beam, not in the column, which is a better way. So we don't have to worry too much about the the plastic hinge formation. And so we select 700 by 700 millimeter for the column. Sometimes you might find you can manage this 600 by 600, but you might select 700 by 700 because we are not losing very much. We are not using a lot of space. If you look at this grid size, it's 6 meters by 7.5 meters as we did last time. So you can select second beam system. I'm not going to mark any second beam system here because it will confuse, it will add to some little bit of confusion. So you can select the slab system either without beams, secondary beams, or with secondary beams. It's totally up to you. But the important point today we have to look is the wall is bending about an axis like that. Column is bending, beam is bending. So I value of is 1/12 into breadth 0.25 into 6 cube. And here I is 1/12 into 0.7 into 0.7 cubed. So what can you say about the I value of wall and I value of column? Wall is much, much, much bigger than I column. So if you look at the deflection of the structure, if it is a cantilever subjected to a dot W, the reflection at the top, delta, will be a function of W L to the power 4 divided by K times EI. K you can find from a textbook. So if you're using this equation, if I is very big in the wall, IW is very big, what can I say about the delta value? Delta will be very small. Delta will be very small. And then you say delta is so small that we say delta is equal to almost 0 because it's only 10-story building. Delta is approximately equal to 0. So if there's no lateral deformation, we will have about 10-15 millimeter deflection because it's a 40-meter tall building deflecting 10 millimeter, very small. So we say building is not deflecting. Building is not moving. So if the building is not moving, why? Wall is not allowing it to move. Then we say all the lateral loads, all these W, will be carried by walls. And the frame carry only the vertical load. Frames will carry only the vertical loads. Now we have simplified the design. To a great extent. Because now all the vertical loads will be carried by the frames. Basically, slabs will transfer the loads onto the beams and beams will transfer the loads onto the columns. So frames are carrying the vertical loads. Walls also can carry the vertical loads, but when it comes to lateral loads, almost all the lateral loads are carried by the walls. So we'll find the wall is carrying a load N and a lateral load W, which causes a bending moment M. So the wall will be carrying a bending moment M and an axial load N. So we can do the design first by designing the frame and then designing the wall. On the other hand, we can design the building by designing the frame first and then designing the wall. So either way, you will get the same answer because now we are divided the problem. The problem is all the lateral loads are carried by the walls, all the vertical loads are carried by the frames. And if there's a wall instead of a column, then wall also can carry some vertical loads. Anyway, there will be the self weight of the wall. Self-weight of the wall is carried by the wall. So wall will have axial load plus any other load transferred onto the wall. So that is the situation. So let's see how to design the wall first. And we'll take y direction. You take y direction. We take y direction. Then we have the second model area as 3 times I. I is this value. IW is this value. 3 times IW. Why 3 times IW? Because we have this wall, and this wall. There are 3 walls. There are 3 walls and a total load of W acting as a UDL along the height of the building. So we have to see how to design the wall. So what we can do is, because the load is W, we can straight away say M is equal to, if the height of the wall is H, height is H, M is equal to WH divided by H by 2 or WH squared divided by 2. Delta times H is the total load, H by 2 is the distance of centroid. So the total moment will be WH squared divided by 2. And the moment carried by each wall will be this divided by 3. So M by each wall 1 will be WH squared divided by 6. So we have 3 walls. So each wall will carry WH squared divided by 6. WH squared divided by 6. And we have to determine this moment at ultimate limit state. So when you are using Euro codes, the W is multiplied by 1.5. W is multiplied by 1.5, considering it's a variable action. Consider that it is a variable action. Consider that it is a variable action. And in another lecture, I'll show you how to get all these different combinations. Today, we'll not worry too much about it because it's a lecture on its own right. So we'll see how the combinations can be formed. But today we'll simply consider that wind load will be multiplied by 1.5. Then we have the dead loads. That is the self-weight. So we multiplied by 1.35, and we can have the wind load acting simultaneously. So we multiply the imposed load by 0.7 according to the Euro code multiplied by QK. So it gives a reduction factor because total wind load and total live load cannot act together. So we have the dominant action and the secondary action. In this case, dominant action is the wind, and so we get 1.5 times wind. And we also have secondary action and imposed load, so we get 0.7 times 1.5. For the dead load, we always get 1.35. Which means now we know the value of N, we know the value of M. So if you know the value of N and M, the important question is, how do you find the reinforcement? How do you find the reinforcement? This is a wall. This is a wall. We know the overall moment, we know the overall axial load. And how do you find the reinforcement? Now I'm going to erase the board. So if you want little time to take down notes, please tell me. Otherwise, I'm going to erase it. because I want little space to show you how the reinforcement can be calculated. So we have combination 1.35 GK plus 0.75 times 1.5 QK, and the wind load is multiplied by 1.5 because wind load is dominant now. But we can have another load combination where the imposed load is dominant. Wind load is 0.5 times 1.5, 50% of wind load plus full live load. That's also possible. So I'm going to erase this all. Because we know the wind, all the loads, now you can calculate you can have numerical values. Then we have a shear wall, which is 6 meters of length, which is bending about an axis like this. Always you can use right-hand corkscrew rule to find how the walls bend, about which axis the walls bend. And then this length is 6 meters. Now you can make another assumption. That is, this is a long wall, tall wall, 40 meters of height, 6 meters of length. Then we assume that this is going to behave as a column. And what we can do is, you can make use of the column interaction chart, NOBH, MOBH squared, and we get charts like this: 0.4%, 1%, 2%, and so on. So what we do is, we select a certain area, something like 0.5 meters, for concentrating all our reinforcement. At the edges, ends, we consider a length of 0.5 meters. So the effective depth will be this height, D will be 6.0 minus 0.25 meters. And then you can find the DOH ratio, which will come close to 0.9. So based on that, you have to select the column interaction chart. So there are column interaction charts for different values of DOH, but in a long wall, it's most likely to be close to 0.9. So based on this, we calculate NOBH, MOBH squared, and then we select a point on the appropriate column interaction chart. And then we say, we are going to provide that amount of reinforcement. And where do you have to provide that amount of reinforcement? That is at the bottom. That is at the bottom. So if you want to reduce the reinforcement, we can see the tall wall, 40 meters tall. You can select different sections and calculate N and M at each level. And then based on that, you can reduce the reinforcement. Based on that, you can reduce the reinforcement. So let's say we find that we need 0.4% reinforcement. Let's say we find that we want 0.4% reinforcement. 0.4% reinforcement. So we say 100 is over BH is equal to 0.4% or 0.4. And then from that, you can calculate AS. And then what we do is we provide half of A is here. Is A is divided by 2. The remaining half here, like what we do in a column. So we concentrate the reinforcement at the ends, and we provide half the reinforcement we calculate here at the corners. Then you have to ask, what are we going to do for the rest? For the rest, we are going to provide the Eurocode says provide 0.2% reinforcement. 0.2% reinforcement, the vertical direction. Whereas the British code earlier used to say provide 0.4% reinforcement. Sometimes you find that 0.2% reinforcement is too light. So generally in Sri Lanka, I think in the Sri Lanka National Annexure also, we will provide 0.4% reinforcement as the minimum. So we can provide 0.4% reinforcement as the minimum, 0.2% on each face, vertically. And horizontally, we can provide 0.25% reinforcement on both faces. Both faces 0.25% reinforcement horizontally. Now you can see the middle part, the reinforcement is already provided using the minimum rule. And at the ends, the reinforcement is provided by considering that it behaves as a column. So now we have provided the reinforcement in vertical direction and horizontal direction. Now the design of the wall is over at the ground level. We can repeat the calculation at any level you want. And you can reduce the amount of reinforcement needed as you go up. As you go up. So this way, we can easily find the reinforcement in the wall by making an assumption that the wall is going to behave as a column. Wall is going to behave as a column. Any questions on this?
So there is one question in the chat box.
Yeah. What is the question?
Do we need to consider notional load or imperfection load with the wind load?
Yes, always you have to consider a notional load. A notional load is given in the Eurocode as well. In the British code, it is 0.15% of the dead load that we call 0.0015. 0.15% of the dead load. But in the Eurocode also, similar rule is given. So you have to use that rule and calculate the value. The values come closer and always consider notional load. That is correct. You have to consider the minimum as the minimum of the value maximum of notional load or the wind load. Whichever is higher, you will use it. But notional load, you don't multiply it by a factor. Notional load is whatever the value you get from the calculation, but you don't have to multiply it by a factor. Whereas wind load, you have to. So you have to. It's better if you consider notional load and wind load all together. So the computer program, computer package, if you are using a computer package, it will automatically select which one is more critical. Otherwise, you have to look at the load magnitudes and decide which one is more critical. It's true that notional load should be used. Any other question?
Yeah, can't we consider the combined second moment of inertia of the core wall? Because here you consider only the major direction, minor direction you didn't consider. So can we consider the combined?
But if you consider the way that it's twisting, it is easier to consider only the major direction, the walls in the major direction only. Because, it's a 10-story building. And the walls in the other direction will contribute very little unless the building is twisting. If the building is twisting, the walls in the other direction can make a significant contribution. Otherwise, when you consider the length of the wall, the dominant behavior will be due to the length of the wall. So generally, what you have to see is, how much accuracy you need for the calculations. And the gain you get, the gain will be very little, and you will be just unnecessarily wasting your time on doing very serious calculations. So that's why, it's important that we can go, when you are doing manual calculations, generally, we do not consider the walls in the other direction. We consider the walls only in the dominant direction and then do the manual calculations. So this is a manual calculation method. On the other hand, if you want to get a more accurate result, you can make a 3D model for the 10-story building. And then automatically the model will take account of the presence of core boxes. So what we call is, these are called core boxes. It's a core which is acting like a box. So automatically the computer program will consider the effect that there's a core box. But when you are doing manual calculations, there is no need. And the error that you get in the answer is very minor. So there's no point in wasting our time trying to do very accurate calculations when you consider that design itself is a very approximate process. Why do I say it's a very approximate process? The only thing that I can assess with a reasonable degree of accuracy is the self-weight. Can I estimate the impost loads? No, I cannot. So I make a guess. Can we calculate the wind loads? Again, the answer is no. So we make a guess based on some guideline given in a code. So if you are guessing so many things, then we include a partial factor of safety to look into the uncertainty of these things that we have guessed. That's why we have a higher factor. So when so many things are approximate, what is the point in being very accurate with the shear wall calculations? No point. So always you have to look at how much accuracy we need in design. And if you think by being little more accurate, you are not going to save anything, don't do those calculations. They are useless calculations. Do a simple model where you will understand the exact behavior. And then if you want a very accurate result, allow it to a 3-dimensional computer program like ETABS. Because ETABS is written for buildings and it can take account of all these. Can take account of all this. So basically, you have to look at the lecture, less than 5 stories, no shear wall, one. Up to 10 floors, another method. When I go, but again, you use a simple model, like a 2D model, converting everything to a 2D model. Whereas when I'm going for a 20-story or more, now it's time to be a little more accurate. And for those things, we will do a 3D model on computer. And it is not a waste of time. It's worthwhile exercise. But trying to do a 3D model for a 10-story building, knowing very well that the deflections are going to be so small, interactions are going to be so small, you'll be just wasting your time. I will consider the foundation design much more seriously than the design of the superstructure, because finally all these loads should be transferred to the foundation. Now we have a big problem. Problem is, do we need a pile foundation or a raft foundation? That is a big question. Because sometimes pile foundation This might have only few piles, but it might cost a lot of money because pile foundation means a lot of mobilization. So we might have to consider a rough foundation, although it's a 10-story building. So if you have lightweight partitions, there's a good chance that a rough foundation may be possible, but you might have to consider a weight compensated raft, where the raft is actually, the building will have 1 or 2 basements, and then the bottom slab of the basements will act like the bottom slab of the basement will act like a raft. Otherwise, you will find that the soil strength is not sufficient. So you may need one basement plus one semi-basement type of situation, provided the water table is sufficiently low. Provided the water table is sufficiently low, you might go for that kind of solution. So one of the assumptions that we take in this model is the shear walls are connected to the foundation, and the rotation at this level is almost zero. At the floor level is almost zero. And assuring that with the foundation design will be a bigger responsibility than considering trying to be very accurate with the superstructure modeling, because superstructure is not going to do much in this particular structure. The reason is there are plenty of shear walls and the reflections are very small. So all the things will be dominated by the behavior of the shear wall, where the shear wall deflection will be very, very small, like 5 to 10 millimeter, which can again be ignored, and the frame will be designed separately. Have I answered your question? Yes, can I get some feedback? Have I answered the question, or you have any other question?
Yeah, thank you, sir.
Yeah, okay. Any
Yes,
other
sir.
question?
Yes, sir. In a wall, so you have designed as a column. So in a column,
Yeah.
so we do restraining of alternative bars, which are 150 millimeter away from a restraint vertical bar. Do we apply that same concept for this wall reinforcement?
No, wall reinforcement, that concept will be applicable if the amount of reinforcement in that particular area is more than 2%. So we calculate this concentrated reinforcement, then calculate the amount of reinforcement in this particular area. If it is more than 2%, then you have to ensure that you detail it exactly as a column, But in my case, I know for sure the first floor and the second floor. These areas will be heavily stressed. So when I'm detailing for about 2 floors, I might consider a reinforcement arrangement like this. So I'll be confining these edges to a size Y. In case of an earthquake, which part of the wall will get the maximum effect? The bottom part will get the maximum effect, and again, even in the bottom part, the ends will get maximum effect. So no harm in having higher confinement. To have higher confinement, for about 2 floors or 3 floors, you can have additional restraints, right? And anyway, because it has been designed as a column, no harm in providing this concentrated reinforcement, the confining reinforcement over the full height, because in case of an unknown, unforeseen situation, some of the reinforcement might be mobilized. Otherwise, theoretically, you don't need What you need is only the spacer bars, which means for every 0.4 meters or so, you'll have a bar connecting the 2 mats of reinforcement. You'll have an additional bar connecting 2 mats of reinforcement. That's all you need. But because you need only a few links like this, I mean, it's not going to cost us much money. But when it comes to the safety enhancement, the benefits are very high. Because of that, you might consider it's worth providing the edge restraining reinforcement over the full height of the building. Over the full height of the building. Have I answered the question?
Yes, sir. Thank you.
Okay. Any other question?
Yes,
Yeah,
one
there
more
are few-
question. One more
I will-
question. So here you are assuming that the geometric center and the stiffness center is same. So due to the
Same.
architectural
Basically,
arrangement,
no, I'm not assuming. I have selected the walls in such a way that it becomes that way.
due to the architectural arrangement, if we can't make it coincide, is it okay? Is it recommended to design with the twisting mode?
No, it's okay if it's a small building. It's okay to design it as a in the twisting mode. But if it is about 10-story building and you cannot do anything, it's okay. But when you are going beyond 20 floors, 10 floors, you have to keep in mind the stuff belongs to the structural. So one way or the other, you will do calculation and tell the architect, I want some extra walls because I want to balance the building. I don't like a twisted building. But if it's a small building, 7-story to 10-story type, and architect is adamant that he cannot give anything, you want to one way or the other finish the structure, then what I do is I will go for a box. Why the box? I'll connect this with a big beam, and I'll put some beams here, and I'll make it very stiff box. What will happen? Now it's a very stiff box. Even if it twists, it can take the twisting very well. It can take the twisting very well. So because of that reason, if the architect is adamant and he doesn't understand the basic fundamentals, but still you want to work with the architect, take some precautions. But don't compromise. If the structure is more than 10 floors, you must be in charge of the structure. Architect is in charge of the facade. Architect is in charge of the facade because he makes it beautiful. Whereas when it comes to the structure, architect should ask the structural engineer, what do you want? And then based on that only, the architect should do the planning, or the architect can do the planning with a flexible mind that, structural engineer asks for something extra because building is twisting. The architect should be willing to give that option. Otherwise, it's too dangerous. There are buildings where the problems are persistent because engineer has given to the request by the architect. That is not the way. When the building becomes taller, structure belongs to us, facade belongs to the architect. So you have to keep that in mind, and don't give in too much, because you might end up with a bad building, and when the bad building develops a bad reputation, who will lose the reputation? You will lose the reputation. So it's not worth. So you will insist that, that the building is, you are allowed to balance the building. You are allowed to balance the building so that the building is not twisting. On the other hand, what you do is then you will make a 3D model of the building and show the architect, this is how this building is going to behave. And do you like that kind of twisting behavior? The chances are architect might back down and say, okay, you select the structure, I'll do the architectural part or the facade around the structure, rather than I'm trying to dictate where the structural members come. The architect cannot decide where the structural members will come. It has to be decided by decided by the structural engineer. Then a general arrangement drawing is drawn. The architect can approve the locations and ensure that the strong elements that you have selected will not coincide with the vision of the architect. So the architect can work with the structural engineer in harmony. So always you have to, otherwise you will tell the architect what's going to happen. And even if he can't understand mathematics, don't use too much mathematics, but tell the architect how the structure is going to behave and why it's twisting and so on. Then he might he or she might help you to come up with the better. Is that clear? If nothing can be done, I'll make some of these super strong, so that even if the wheel twists, it twists very little, so that nobody will feel that it's twisting. Is that clear?
Yeah, thank you, sir. Thank you.
So design of wall is very simple. Now we have to design the frames for vertical loads. Shall I move to design of frames with the vertical loads?
Yes, sir.
Yeah.
So can I ask
Yeah, any other
what-
questions?
Sir, then from where we can find these column interaction curves? Should we have another set of curves which are not
Actually,
available?
there's a structural engineers, the Institution of Structural Engineers has issued a manual. And in that manual, you can find all the interaction curves for Europe. And there are other interaction curves, it's freely downloadable from internet. You can download it on the internet. The interaction charts are available on internet. You can download it.
Thank you, sir.
Okay.
Another one.
But
thank
these,
you.
those interaction charts will have FCU, CK term also, right? But it doesn't matter. They are all the same, because rather than developing different charts for different concrete strengths, they have developed one chart up to 50 megapascal concrete. Any other question?
There are a few. I will read out. I think.
Yes, please.
Yeah. How do we select the depth of the wall sections of the two ends? One question. Other one, do we need to consider slenderness in these wall designs when designing as column?
Good questions, yes. So basically, it's a little bit of judgment, because you don't like too small and too big. So if it is 6 meters, you might consider even 0.75 meter or 0.8 meter ends rather than 0.5 meter ends. So it's totally up to you, because when the column is behaving, it will go into a plastic behavior, not the elastic behavior. So in the plastic behavior, what matters is where the main reinforcement are. So it's not an elastic behavior. At the failure load, the wall will have a plastic behavior. So it's a cracked wall, because the wall is cracked. What you need is a concentration of reinforcement at the ends. So it is so purely arbitrary. So you might design the same wall with 0.8 meter. Another person might design it with 0.7 meter. I would say 0.5 meter is the bare minimum. I would consider something like 0.7 or 0.8 meter. But you will not consider 2 meters, because too much. 2 meters is too much. So anything up to 1 meter is okay. Anything up to 1 meter is okay, but I would prefer something like 0.8 meters, because it's only a small buildings, 10 floors only, and the walls are 6 meters of length. So because of that reason, I might consider something like 0.8 meter, or even 1 meter is okay. That is first question. Second question is, how about the wall buckling? But if you consider this building, it's a brace building. In a brace building, the effective height is about 0.85 times the clear height. And when you consider that, you'll find that the walls are all behaving as short walls. Because you can go up to a ratio of
Can't hear, sir.
Can't hear, I think, Prof.
Professor, unmute your phone. Can't hear. So,
We can't hear you, sir.
Professor, we can't hear you.
I think he even don't hear us.
Yeah, yeah. Madam Kamala, can you tell him? Unmute your phone.
Are you muted now?
No, no.
I think he has logged off from the phone. He has left from the meeting from his phone.
Recording in progress.
Professor, last 5 minutes we couldn't hear you.
The point we talked about the slenderness, we didn't hear.
Again, he's muted. Again, his phone is muted.
No.
yeah, you can hear me, right? You can hear.
Yeah. Now can, but
Yeah. Oh, yeah. Okay, because there's a small problem. I have been disconnected by the phone.
yeah.
Okay, so I will draw this. Now the frame.
Excuse me, sir.
Now the frame. So one of these frames. So what we do is we select a simplified subframe and right. So I'm going to make a simplified subframe by adding fixity at these locations. So simplified subframe will look like this. To look like this. So I can go for pattern loading. That means in Eurocode, we consider all the spans are loaded by 1.35 GK. For dead loads, all the spans are loaded. But when it comes to the live load, we can say, here we get the live load, here we get the live load, and so on. So Eurocode actually specifies one thing: the national hash of UK specifies the alternative the alternative spans loaded maximum. So in Sri Lanka national hash also we have gone along with the UK pattern, UK method. So we can still use all the spans loaded full or alternate spans loaded with maximum and others are not loaded. That can be decided. So how do we analyze this? Easiest thing is to analyze it using a simple software like SAP 2000. So you can make a model of this subframe on SAP 2000. And then the most important thing is here you have to make sure rather than fixity, it is like a joint like this. That means this particular joint can't move, but it can move vertically. It can move vertically. It's important that you assign a joint like that. Don't assign a fixed joint. Assigning a fixed joint means the column is fixed. It's hanging from the sky, which is wrong. So always you have to make sure the column joint at the top will be a moving joint, not a fixed joint. Not a fixed joint. It's important. Always allocate a moving joint in the vertical direction. But what happens is all this will shorten, and if this point is fixed, then the frame will start hanging from the top of the column, which is wrong. This is not going to happen. So you have to introduce a joint like this. So you'll create pattern loading, use SAP 2000, create bending moment envelope, and do the calculation. Again, when you are creating the bending moment envelope, you can consider moment redistribution of moments. So how that happens is you will make sure that what if you get a bending moment diagram like this, you can say only 80% of the moment will act here. So that means you change the origin of the line, bending moment diagram.
We can't hear again, sir.
Can't hear again.
Professor can't hear again.
We can't hear, sir.
Excuse me, Professor. They can't hear.
His connection is not there. He is not there.
His connection is there, but
The phone is not there.
that's the thing. That's the thing. Yeah,
His phone is gone.
phone's gone. Yeah, screen is there, but his voice connectivity is gone. How can you explain?
You have to inform to sir only.
I'm again getting a small problem with the.
No, it's okay.
Yeah. Can you hear me now through the computer?
Yeah, now it's clear. Yeah.
Oh, yeah, today is a dialogue problem. The phone is disconnecting. Can you hear me?
Yeah, yeah.
Yes.
Recording in progress.
No echo.
Mm.
Sorry about that trouble. Again, there was a small technical problem. I have been disconnected due to not sure which is the problem. I think you have not heard the part on moment redistribution.
From that menu movement diagram, you can repeat again, Professor.
Yeah, okay, right, okay. So what happens is, codes allow up to about 30% redistribution, but generally I would not do more than 20% redistribution. So redistribution means we are reducing the bending moment over the support and then allowing it to be compensated by increasing the bending moment. So basically what you do is you calculate 80% from the top and mark a point and get the baseline acting through that point. So that way you can very easily use a graphical method and calculate the value of the bending moment relevant for your calculations. So rather than doing any numerical calculation, you just use graphics and select the values. That's very easy. So the whole idea of moment distribution is the beams cannot collapse by forming plastic hinges because beams are supported by the column. So at the support, there's no point in designing for the full moment. You can design for about 80% of the moment, where the remaining part of the moment is now taken by the span sections. So you can see the span sections will now be designed for a higher moment than earlier. But span sections are very efficient in carrying moment because they behave as flange beams. So because of that reason, there's no harm in transferring part of the moment at the support to the span. So basically, you will go for pattern loading, generate bending moment diagram, and then find the critical moment diagrams, and then you can reduce the moments in critical moment diagrams. The most critical moment diagram will be all spans loaded with maximum. And once you select that, you can reduce it by about 20%. So you can do moment distribution once you get the bending moment values. And generally, where do you get a failure in a beam? You never get a failure here because it's supported. Always you get the failure here. So when you're calculating the reinforcement, will you write exactly the answer, or will you provide little more reinforcement in the span sections? I would always provide little more reinforcement in the span sections, because nothing can go wrong when you provide little extra reinforcement in the span sections. The reason is any failure in the beam will occur in the span sections. So I would like to have a slightly higher factor of safety where the failure can occur, and I will go for a lower factor of safety at the places where the failures cannot occur. Is that clear? Is that clear?
Yes, sir.
Yes, Professor.
Yeah.
Yes, yeah.
Yeah. So this is not a normal design where this is a design where you like to assess the risk and take some extra precautions that are not given in the code. So you take some extra precautions that are not given in the code. And that extra precaution is you will over design the span section slightly, whereas you will do moment distribution to a reasonable level over the support. That is always there. But codes do not say assess the risk, and if you anticipate any higher risk, then provide some extra precaution. That part is missing in the codes, but when I design, I always consider anywhere, any place where the failures can occur, I will take on my own code, I will take few precautions, like using higher level of reinforcement, slightly higher level of reinforcement. Is that clear?
Excuse me, sir.
Yeah.
Sir, that if we consider that earthquake load, so
yeah,
if we redistribute the movement at the column beam junction, so then the reinforcement density reduced. Then that plastic hinge can be occurred at the column beam junction due to that earthquake load.
No. Actually, the column section is bigger than the beam. Always the plastic hinge will.
Professor, we can't hear you.
Cannot hear.
earthquake. Is that right?
Professor couldn't hear for some time now.
Yeah. There was a question on earthquakes. And what will happen when you do the redistribution in case of an earthquake? So what happens is, with redistribution, we are reducing the bending moment at the support, and the bending moment in the beam is reduced. By about 20%. Then the question is, what will happen in an earthquake? In an earthquake, still the hinge will form in the beam because beam has a smaller cross section than a column. I deliberately do still the plastic hinge will form in the beam. So to have satisfactory behavior with respect to the plastic hinge, what is important is the confinement provided by the links, not the longitudinal reinforcement. So by reducing the longitudinal reinforcement or the support, you are not going to reduce the earthquake resistance. Earthquake resistance confinement that you have provided at the support. So if you have provided reinforcement at about 75 millimeter centers, that is the rule I always use. For about 0.6 meters, I use reinforcement, T8 reinforcement at 75 millimeters. Automatically, you will find the confinement is high. Because the confinement is high, the behavior of the building where the redistribution has been undertaken and no redistribution has been done, both will be the same. The reason is it's not going to the land is not going to govern anything. It's a transfer. Because of that reason, I generally have a rule. The rule is I would like to have, for about 0.6 meters, I'd like to have T8 bars at 75 millimeter centers. So that means a lot of T8 bars, lot of confinement, then the earthquake resistance will be there. Have I answered the question?
Yes, sir.
Excuse me, sir.
Yeah.
Sir, code has a limitation on redistribution amount. If the frames provide lateral stability, then the code says the maximum amount is 10%.
That is unbraced. The frame providing lateral stability means it's an unbraced structure. But here it's a braced structure. Because we are having shear walls, it's a braced structure. If it is unbraced, 10%. If it is braced, you can go for up to about 30%. But generally, I would like to stay somewhere around 20%. Is that clear?
Clear, sir. And another thing, sir, when we do the when we design for the span, are we going to consider flange section to design a span? Or if we use rectangular section design, still we need to provide additional reinforcement?
No, I mean I would always go with a flange beam design for the span because it's very economical. I will not design the span section as a rectangular section because it's going to behave as a flange beam. I will always design it as a flange beam. Is that clear?
Clear, sir. Clear.
Yeah.
Excuse me, sir.
So any other specific question? Yeah, go ahead.
Hello, sir.
Sorry?
Sir, when the beam has different section, that means one continuous beam has different sections.
Yes.
Is it good or the next question is if there's a different section due to the architect purpose, doing moment redistribution is good.
Actually, even if you have different section, if you want, because when you are calculating the bending moment values, already this variable section is taken into account. This is organized by the computer program with different beam sizes. So even if there's a different beam sizes, there's no harm in doing a momentary distribution. But I might stay somewhere around 15%. Rather than going for something like 20 or 25%, I might stay somewhere around 15%, because now the structure itself is not very consistent. You know, we have in different sections. So there may be anchoring problems and all that. We really don't know how we are going to detail it. So better to keep the moment distribution at a certain level, so that the not too much moment is transferred to the span sections. But you can certainly do the moment distribution. It does not matter, because when you are doing the bending moment analysis, automatically the computer program will take into account the different sizes of the beams. It's not a problem. Is that clear?
Yes, sir. Thank you. Sir, another one, sir. Then within the span, if the section is changing, will it cause any local failure? That means not a trapezoidal change, it's a sudden change.
What do you mean by that? Within the section, within a span, you are having different sections.
That means rather than changing, the section is changing within the column, it's changing at the middle of the span.
Due to some architectural reason, you are having two different sections.
Yes. Is it
in that
is
case?
it a good one?
No, in that case, when you are modeling, you will model it as a smaller beam. When you are modeling, you will do the modeling as if the whole beam is a smaller beam, not the bigger beam. Is that clear?
Sir, thank you.
Okay. Right.
Sir, excuse me, sir. So
Yes.
should we design our shear walls as brace one or unbrace one?
No, because you are having shear walls in two different directions, X and Y. All the shear walls will now be braced. But if you have shear walls only in one direction, then you are asking for trouble. I will ensure that always I will brace the building in both directions.
Right.
Is that
Thank
clear?
you, sir. Thank you, sir. And the one said now these beams are a little deeper and wide, and when they connected when they are connected to this 200 millimeter or 225 millimeter thick shear walls, is there any problems with the overall behavior?
The slabs. So when you are connecting the slabs to the wall.
I mean, sir, beams to the wall. Slender wall.
Beam to the wall. Beam to the wall. At some places, instead of the column, you are having the wall. That is your question. Is that right?
So wall thickness is smaller than the beam width.
So it doesn't matter because if you can provide enough bearing, in the case of wall, now you can see if you take here. Now there are walls in both directions, so it will not be a big problem. But if you don't have the wall in the other direction, then you have to be little careful in detailing. Generally, we don't consider, because wall is a very strong element. So if you connect the beam reinforcement and send the beam reinforcement into the wall, there's very little chance for it to fail. So because of that reason, we will not worry too much about this connection, because we consider it's a proper connection. The answer comes from the fact that we are going to provide sufficient reinforcement in the beam so that it can be properly connected to the wall. So because of that reason, I don't anticipate any problem there. Is that clear?
Yes, sir. Thank you. Thank you very much.
So make sure the beam reinforcement continue into the wall. That is the important point.
So excuse me.
Yeah.
So sometimes actually I want to know whether it is necessary to go for higher stiffness beam than column always, because sometimes we have to select the dimensions of the beam compared to the column, having lesser having some higher stiffness than column.
Actually, what you have to make sure is column is larger than the beam, not vice versa. So you select the size of the beam, and last time I explained how to select the size of the beam. I said, under different situations, even for a higher spans, we use say 600 millimeter overall depth, and then if you have any problem in the other direction, then you can actually select a suitable beam size. So basically, the whole idea is ensure the column is bigger than the beam. Column is bigger than the beam, not vice versa.
Okay, sir. Thank you. Another question.
Then you can confine the failure to the beam. Plastic occurs in the beam, and beam is okay because beam has a higher capacity in the span section, so it's okay to have the plastic hinge forming in the beam.
Yeah.
But if the plastic hinge forms in the column can start moving and losing the stability.
Yeah, exactly. Yes, sir.
Like a bigger column and a smaller beam.
Yeah.
Now we are approaching 8:30, and if you have, I think we can take only about 1 or 2 questions more. So basically, once you know the bending moments and shear forces, you can destroy the reinforcement in the frames. And the columns, from this frame analysis, column loads can, the column load transferred onto the load transferred onto the column at each flow can be determined by using the subframe. And based on that, you can do a quick manual calculation and find the load on the maximum load on at the base level.
Yeah.
Because you can always find the load that is transferred onto a column by the beams when you do the subframe analysis. So based on that, you can make a estimate of the column load. So otherwise, you can go for the tributary area and do the calculation. You can go for the tributary area and do the calculation. So the tributary area and do the calculation. That is also possible.
Yeah. Okay, so thank you, sir. Another question, sir. Sometimes when we change the redistribution level, and the point of contraflexure get changes, how can get some idea?
No, it's only a minute change. So Eurocode gives a lot of guidelines on those things. So basically, what you have to say is why we don't want to continue too many reinforcement across the column is we have congestion of reinforcement, right? Yeah. So if you think the point of contraflexure is changing, you can actually make it make the cutoff points. You can adjust the cutoff points, reinforcement cutoff points, and be adjusted. So in such situations, I would rather than trying to do a lot of accurate calculations, I would rather use a simple rule. One rule I generally use is I will make sure that all the bottom reinforcement continues up to about 0.3 within 0.3 meters of the support. Within 0.3 meters of the support, then all these minute problems will be looked after. Did you get the point? I mean, I will ensure, because we are not saving a lot of steel by by trying to find by finding the exact cutoff point. We are not saving a lot of steel.
Okay, sir. The reason for asking that question is we don't know how can it affect to the service criteria.
No, basically, if you continue the reinforcement, then there's no way the service criteria will be Is that clear? I mean, what you do is interest when you are curtailing the reinforcement, bottom reinforcement. But no need to be generous when you are curtailing the top reinforcement.
Okay.
Yeah.
Okay, sir. Thank you very much, sir.
So basically, in the beam, I would be little generous with the bottom reinforcement.
Yeah.
Because any failure in bottom reinforcement will end up with a crack.
Yeah,
That's
yeah.
why I said, I like to do a risk-based analysis. Risk-based analysis, not just analysis. I will not believe in the results, but I will look at how the structure behave, where things can go wrong. At places where things can go wrong, I'll put some additional reinforcement and ensure those places will never ever fail. That's my philosophy.
Okay, sir.
Okay.
Okay, sir. Thank you. Thank you very much, sir.
Professor,
With that,
there was
shall we
a,
end the,
yeah, Professor, there was a raise hand situation from Sakuni for some more time. So shall we ask her to ask a question?
Yeah, of course, yes.
It's okay. It's okay because we didn't hear. That's why I just raised hand. Someone test.
All right. Okay. Now it's okay. Okay, right. Yeah. Then shall we wind up? Because I have covered almost everything. I mean, I have showed you that it can be done easily. Once you understand how it behaves, it can be done. But this philosophy will not be applicable for 15 to 20 story buildings. So next day we will think how to deal with 15 to 20 story buildings. Right? But what you have to keep in mind is, if you want, you can do a computer model for all these structures and get the answers. But sometimes, when it's a small building, people ask questions suddenly. Then you can do a quick set of calculations like this and come up with answers. Right? But otherwise, always go for a 3D model and do the analysis. But it's worth knowing how to deal with a small building, a small base building, so that you can even when you don't have a computer or you don't have access or you are in a hurry, you can always beat the computer by doing calculations like this. But after that, once you sort the problem out, you can go for a computer model and do the proper calculations. But the important thing is to understand how the structures behave. So with that, shall we conclude?
Excuse me, sir.
Yeah.
Sir, is it necessary to continue beams through the shear walls, or can we stop at the end of the shear wall?
No need to continue, but you have to provide sufficient anchorage into the shear wall.
As a fixed joint.
To ensure that the joint behaves properly. Otherwise it will become a simply supported pin joint. If you don't provide the reinforcement properly. And then it will transfer higher bending moment to the span.
Excuse me, sir. One last question.
Thank you, sir.
Yes.
Sir, do we need to the bottom line of strong column weak beam condition is whether the stiffness of the beam and the column, IOL ratio, or every time do we have to consider the larger column and the
basically columns will not form hinges because column has a bigger section in compression. So because of that, columns, if the column is large, always the hinge will be in the beam. Columns will not form hinges because most of the area of the column is in compression. So always the hinge will form in the beam, not in the column.
So
have I answered your question?
I have one doubt. If the column has a higher IOL ratio and the beam has less IOL ratio, do we need to consider the IOL ratio or the dimensions?
No, it is the dimension. It is the dimension. Because column, you have to, that's why I said column, although column is longer, the IOL ratio is different, but still when you consider reinforced concrete, beam concrete is cracked, column concrete is almost uncracked. Because most of the column is in compression, column concrete is uncracked. So because of that reason, always the tendency is to form the plastic hinge in the beam. Okay?
Okay, sir. Clear.
Okay. With that, we will conclude. Yeah?
One more raise. Yeah, one more raise hand from Umapati. I think, are you there?
Yeah. Yes.
Yes, Umapati.
Yeah. for the core wall, if we confidence about the bracing on all direction is firm, can we consider as a box section when we calculate the second moment of inertia? It's a hollow
Yes,
section.
you can. And in programs like ETAS, you can actually make it happen. But when you're doing manual calculations, it's not worth trying to do so much extra calculations. So why you do manual calculations is you want to get quick answers. So in quick answers, so you can get quick answers by doing simple calculations. So don't try to make the calculations very complicated because nobody is going to, give you more credit these days. Always keep the calculations simple.
Thank you.
Because if you try to make things complicated, you will never be able to construct buildings like Altair. But there are a lot of complications within the building itself. So if you make your calculations also complicated, then it will be impossible. So that's why we go with 3D model with proper 3D modeling methods. Program will capture most of this integrated by the program. So we don't have to really worry about it. Okay?
Oh, thank you, sir.
Yeah.
Sir, excuse me. That each time medial column size is greater than corner column size. But when I do design SAP also doing that way, no sir, then each column also different size. That's what is the opinion.
I really don't like that because, when you are doing the construction, it's so easy to have the same column size for all the columns. Then you can easily interchange the shutters. Otherwise, you have to have so many different sets of shutters. It's not worth. Right? It's not worth having different column sizes. I would use the same column size. Yeah.
Sir, but load is a come different.
Yeah, it doesn't matter. It doesn't matter. I would rather try to keep the same column size everywhere, unless it's absolutely necessary to have different size.
Okay, sir. Thank you very much.
Right. Okay. So with that, shall we conclude?
I think, yeah.
Okay, sir, can you reduce the column section in top?
What is the question?
Can you reduce the column section in top floors?
Again, in a 10-story building, I might not do it. But with a 20 or 30-story building, certainly yes.
Yeah.
But in a 10-story building, it's not worth trying to make the columns too small because even the smallest column you can have will be only about 500 by 500.
Yeah.
So you have to change the shutter and do many things. So I really don't know whether it's worth.
As the same question is in the chat box, I think since you answered the previous question, so the same question is there in the chat box.
Right.
I think we've done everything.
Yes, of course.
Yeah. Shall I call Engineer Trimavitan to the
please.
Your vote of thanks, since it's a marvelous with some difficulties, but we managed to do it, so we'll improve next time.
Okay.
Thank you. Good evening, everyone. I'm Trimavitan, a member of the Knowledge Sharing Subcommittee of Civil Engineering Sectional Committee. And it is an honor for me to deliver this vote of thanks now. Today, the third lecture of medium-rise buildings design and construction, explaining the design philosophy for a medium-rise building of about 10 floors has now completed. A big thank to you, Professor Jayasinghe, for your most worthy lesson delivered today. Also, I thank the organizing subcommittees, the presentation and knowledge sharing of Civil Engineering Sectional Committee for this session. I extend my sincere thanks to the ISL for hosting this and the IT teams for your support. Finally, I thank you all our members who participated in this, and I hope you extracted essence of this valuable lecture this evening. Next presentation will be on coming Tuesday, 4th January at 7 p.m. If the time change, so we'll inform you in advance. Thank you, everyone. Thank you very much. Good night.
Thank you very much. Thank you.
Okay, good night.
Thank you very much, sir. How to get that video?
videos will be uploaded to the YouTube, and last 2 videos also already you can see it from ISL YouTube channel. This one also will be uploaded very soon.
Okay. Thank you very much, sir.
Thank you.